Why we need a tornado. Scale tornadoes can last only seconds or minutes, making them hard to measure directly. Wind instruments, like anemometers, often get destroyed in the storm itself. Even mobile Doppler radars, which sometimes capture peak winds, can't always be in the right place at the right time. So, how do scientists know if a tornado was weak or violent? They work backwards from what's left. If a tornado flips over a car, they can estimate the wind needed to do that. If it sweeps away a well-built house, they know they're looking at winds over 200 miles per hour. A standardized scale allows meteorologists to record tornado history, compare storms, and understand risks across different regions. Without it, we'd only have vague descriptions like a really bad tornado or a small one, which aren't helpful for science or safety. The origins of the Fujita scale. The first version of the scale was created in 1971 by Dr. Tetsuya Theodore Fujita, nicknamed Mr. Tornado. He was a Japanese-American meteorologist fascinated by storm damage patterns. Fujita noticed that different types of destruction corresponded with different levels of wind strength. His original Fujita scale rated tornadoes from F0 to F5, and F0 meant light damage, like broken branches, while an F5 meant total devastation, like houses wiped off foundations. For the first time, scientists had a way to classify tornadoes systematically. But as time went on, researchers realized some of Fujita's wind speed estimates were too high. For example, a house might be leveled by 180 miles per hour winds, but Fujita's original scale said it would take 260 miles per hour. The science needed an update. The Enhanced Fujita (EF) scale. In 2007, the United States adopted the Enhanced Fujita scale. This modern version fine-tuned Fujita's work by using engineering studies, better wind damage data, and updated building codes. Instead of just saying, that building fell, so it must be an F4, scientists could now reference a more detailed set of indicators. The EF scale still ranges from EF0 to EF5, but the wind speed estimates are more accurate. For instance, an EF5 now starts at 200 miles per hour, not 261 miles per hour, like in the original. This makes it more consistent with what we know about construction strength and wind physics. Damage indicators. Explained. One of the biggest improvements of the EF scale was the introduction of damage indicators. There are 28 different types of structures and objects used as references, everything from single-family homes and schools to power poles and trees. Each indicator has degrees of damage that range from slight damage to complete destruction. For example, if a well-built house loses only part of its roof, it may be rated EF2. If the same house is completely leveled and only the foundation remains, that's EF5. If hardwood trees are stripped of bark, scientists know winds had to be at least EF4 or EF5 intensity. This method allows tornadoes to be rated with much greater precision than before. EF0 tornadoes, 65 to 85 mile per hour winds. EF0 tornadoes are the weakest, but they still cause problems. Winds of 65 to 85 miles per hour can peel shingles off roofs, push over fences, and snap small branches. Cars might get lightly damaged, and poorly built sheds can collapse. While EF0 tornadoes rarely cause fatalities, they still cost millions in property damage every year. Example: many brief tornadoes in the US plains states each spring fall into this category. People sometimes underestimate them because they don't look scary, but even EF0s can injure people caught outdoors or driving. EF1 tornadoes, 86 to 110 miles per hour winds. At EF1 strength, tornadoes become more serious. Mobile homes can be overturned, larger trees may snap, and cars can be pushed off roads. Roofs on standard homes may be partially torn off, and utility poles might lean or break. Example: in 2019, an EF1 tornado in Ohio left a trail of roof damage and uprooted trees across several neighborhoods. While not catastrophic, it disrupted thousands of lives and highlighted that moderate tornadoes still require caution. EF2 tornadoes, 111 to 135 miles per hour winds. EF2 tornadoes are classified as strong. They can rip roofs off well-constructed homes, collapse walls, and toss cars short distances. Large trees are often uprooted, leaving behind scarred landscapes. These storms can destroy parts of neighborhoods in just minutes. Example, in April 2011, Tuscaloosa, Alabama, experienced multiple tornadoes during a historic outbreak. Some EF2 tornadoes struck rural areas, leveling homes and causing dozens of injuries. While overshadowed by the EF4 and EF5 monsters that day, the EF2 storms still left lasting scars. EF3 tornadoes, 136 to 165 miles per hour winds. At EF3, tornadoes become severe disasters. Entire stories of houses can collapse, shopping centers can be heavily damaged, and cars become airborne. Steel frames and buildings may begin to fail. Example, in March 2020, an EF3 tornado struck Nashville, Tennessee, destroying hundreds of buildings and leaving 25 people dead. Entire communities were reshaped in a single night, showing how even mid-range tornadoes can have tragic outcomes. EF4 tornadoes, 166 to 200 miles per hour winds. EF4 tornadoes are violent. At this level, even well-built homes are flattened, vehicles can be thrown hundreds of yards, and concrete structures may suffer serious damage. The destruction paths are wide and often several miles long. Example, in May 2013, Moore, Oklahoma, was struck by an EF4 tornado. The storm destroyed entire schools, homes, and shopping areas. Tragically, 24 people were killed, including children. The Moore tornado became a national story, showing how tornado preparedness is essential in vulnerable regions. EF5 tornadoes, over 200 miles per hour winds. The EF5 is the category that is both the most destructive and the rarest. As a result of these tornadoes, neighborhoods are removed off the map. Not only are solidly constructed homes obliterated, but they are also entirely carried away from their foundations. Debarking trees, ripping asphalt off of roadways, and transporting enormous debris some distance away are all things that can happen. By way of illustration, the tornado that struck Joplin, Missouri in 2011 was an EF5 and resulted in the deaths of 158 people and damages totaling $2.8 billion. The recovery process took years, and entire hospitals and communities were leveled as a result of the disaster. Even though EF5s are cataclysmic catastrophes, we are fortunate that they are exceedingly uncommon. Why the EF scale matters. People who are not scientists can also use the EF scale. The severity of a storm can be determined with the help of this tool, which is utilized by emergency management, insurance companies, and government agencies. It is helpful in determining building codes, recovery funds, and disaster relief when it is known whether a tornado experienced an EF2 or EF5 rating. People are immediately aware that an EF4 or EF5 indicates widespread destruction, which is another way in which it influences public perception. Limitations of the EF scale. Although the EF scale is extremely helpful, it is not 100% accurate. The fact that it is dependent on damage means that a tornado that rips across the countryside and does not destroy any structures may be undervalued, even if the winds that it produces are extremely strong. On the other hand, a home that was built badly and was destroyed by a tornado with an EF1 rating would appear to have EF3 damage. Weather forecasters frequently blend EF ratings with information obtained from mobile Doppler radar and observations from storm chasers for this reason. Even though technological advancements are still being made, the EF scale continues to be the most reliable method for evaluating tornadoes after they have already occurred.